The river does not look dangerous. At first glance, it appears almost peaceful, a wide stretch of moving water reflecting the sky like glass. The surface glides forward in silence, bending gently around the landscape. No crashing waves, no violent splashes, nothing that suggests immediate danger. And that is exactly what makes it deadly. Because in certain rivers, the most dangerous force is not what you see, but what you don't. There is a moment just before everything changes when the illusion holds. The current seems manageable, the water feels stable, a person steps in confident, maybe curious, maybe unaware. Then, without warning, the ground disappears beneath their feet. Not because of depth, but because of motion. The water does not simply flow forward. It folds, it rotates, it collapses inward on itself with invisible precision. And in less than a second, the human body is no longer standing, it is being controlled. Pulled sideways, dragged forward, then down. This is not panic, not yet. This is physics. Across the world, there are rivers where survival is measured not in minutes, but in seconds. Locations where trained swimmers have failed, where rescue teams hesitate, where even experts acknowledge a simple truth. Once the water takes control, escape becomes a matter of chance. These rivers exist on every continent. Some are hidden deep within remote canyons. Others flow directly through populated areas. Some appear violent at first glance, but many do not. And that is where the danger begins. Because the human brain is wired to assess risk visually, we look for movement, noise, chaos, signs of instability. But violent rivers often present the opposite. They are quiet, controlled, deceptively calm. And beneath that calm surface lies one of the most powerful natural forces on Earth. To understand why, we have to abandon the way we normally think about water. Because rivers are not just bodies of water. They are systems of energy. Every drop moving with purpose, shaped by gravity, terrain, and resistance. Every curve, every rock, every change in elevation influencing how that energy behaves. And when those variables align in a certain way, the result is something far more dangerous than speed. It becomes force. Force that can overpower muscle. Force that can disorient the human body in seconds. Force that does not give warnings. The first recorded accounts of deadly river currents date back centuries. Early explorers described waterways that behaved unpredictably, rivers that seemed to pull downward, trapping anyone who entered. At the time, these stories were dismissed as exaggerations. Today, we know better. Modern fluid dynamics has revealed the truth behind these phenomena, and the reality is far more precise and far more dangerous than early observers could have imagined. In controlled experiments, researchers have measured the forces generated by fast-moving water. Even at relatively low depths, the pressure exerted on the human body can exceed what most people can resist. At just knee depth, strong currents can destabilize footing. At waist depth, the force increases exponentially. At chest level, control is nearly impossible. But depth is only part of the equation. Velocity, the speed of map of the world, suggests order. Blue lines cut across continents, flowing from mountains to oceans, following predictable paths shaped by gravity and time. Rivers appear familiar, natural, stable, even comforting in their repetition. But the reality is far less orderly. Because scattered across the planet are rivers that defy expectation. Systems of water that behave in ways that should not be possible under normal conditions. Rivers where the rules of flow, safety, and predictability begin to collapse. And these are the rivers that do not just move through landscapes. They reshape them. In remote regions of the Amazon basin, river systems shift course so dramatically that entire forests appear displaced within decades. In mountainous regions of Asia, narrow waterways accelerate through confined rock corridors, turning calm streams into violent torrents without warning. In Arctic zones, meltwater rivers carve unstable channels through ice sheets that change shape seasonally. But among all these systems, the most dangerous are not always the largest. They are the ones that appear ordinary. Because a river does not need to be wide to be powerful. It does not need to be deep to be lethal. It only needs one condition to become something entirely different from what the eye perceives. Energy imbalance. A river is, at its core, a moving system of energy. Gravity pulls water downhill. Terrain guides its direction. Friction slows it down. But when those forces stop balancing evenly, something changes. The river stops being a passive feature of geography. It becomes an active force. This transformation often begins in silence. A narrow canyon where water is forced between tight rock walls. A sudden drop in elevation hidden beneath an otherwise calm surface. A submerged obstruction that redirects flow beneath the visible current. Each of these conditions introduces instability into the system. And instability is where danger begins. One of the most deceptive characteristics of extreme river systems is their ability to hide energy beneath calm surfaces. To an observer, the water may appear slow, smooth, even shallow in places. But beneath that surface, flow velocity can increase dramatically. Water moving through confined spaces behaves differently than water in open channels. It compresses, it accelerates, it collides with itself, generating turbulence patterns that are not visible from above. These are the conditions that create what experts refer to as hidden hydraulic zones, areas where water circulates in loops beneath the surface, trapping anything caught within them. Historically, such locations were not understood. Early explorers navigating unfamiliar terrain often recorded incidents where boats or swimmers simply vanished in sections of river that appeared harmless moments before. With no scientific framework to explain these events, the rivers gained reputations as cursed or unpredictable. In reality, they were neither. They were predictable systems operating under complex physical laws that were simply not yet understood. Modern hydrology now allows us to analyze these behaviors with precision. Using satellite imaging, flow simulation models, and underwater mapping, scientists can identify areas where river energy becomes concentrated. What they find is consistent across different environments. Whenever a river is forced through sudden constrictions, such as rock gorges or artificial channels, velocity increases dramatically. When that fast-moving water encounters a drop or obstruction, it creates rotational flow patterns beneath the surface. These patterns are not random. They are structured. A continuous cycle of downward pull, backward motion, and recirculation. To a human caught inside it, this system feels like being held in place by an invisible force. Not pushed away, not carried forward, but held. This is one of the reasons river accidents are often misunderstood. From the outside, it may appear as though a victim is simply caught in strong current. But in reality, they may be trapped in a closed hydrodynamic loop, unable to escape the cycle of motion. The most dangerous aspect of these systems is not their strength. It is their predictability. Once formed, these flow structures maintain themselves until external conditions change, such as water levels dropping, obstructions shifting, or flow direction altering. This means that in many rivers around the world, the danger is not temporary. It is structural. In some documented cases, low-head dams, man-made structures designed to regulate water flow, have unintentionally created some of the most hazardous hydraulic environments on Earth. From the surface, they appear harmless. Water flows smoothly over a uniform edge, creating a soft, even curtain. But beneath that curtain lies a powerful recirculating current, a submerged rotation system that pulls objects downward and then pushes them back toward the structure again. These systems have been responsible for countless accidents, not because they are unpredictable, but because they are visually deceptive. There are no dramatic warnings, no visible chaos, only a smooth, continuous flow that hides a violent internal mechanism. This contradiction between appearance and reality is what makes river systems so dangerous. Humans are visually oriented creatures. We rely on surface information to assess risk. If water looks calm, we assume safety. If it moves gently, we assume stability. But rivers do not communicate danger through appearance. They communicate through energy. And energy is invisible. In natural canyon rivers, this energy becomes even more concentrated. Narrow geological formations force water into tighter channels, increasing pressure and speed simultaneously. The result is a high-energy flow system capable of sudden transitions from calm to violent behavior within seconds. A person standing at the edge of such a river may see nothing unusual, but a small change in footing, a slight shift in position, or an unexpected step into a deeper channel can place them directly into the fastest-moving section of the flow. And once inside that section, the environment changes instantly. The ground disappears. Balance becomes unstable. Orientation becomes distorted. And the river begins to dictate movement. At this point, survival is no longer about strength. It is about timing. And in many documented incidents, that timing is measured in seconds. But perhaps the most unsettling truth about these rivers is that they are not rare anomalies. They are common features of natural geography, found in nearly every mountainous region, present in river deltas, hidden in urban waterways modified by human engineering. They exist wherever water is forced to move under constraint, which means the potential for violent current systems is not limited to remote wilderness. It exists wherever rivers exist. And this realization changes everything, because it means that the boundary between safe and dangerous water is not geographical. It is conditional. A river is not inherently stable or unstable. It becomes one or the other based on flow conditions that can change without warning. Rainfall upstream, sudden snowmelt, structural changes in riverbeds, human intervention in water pathways. Each of these factors can transform a calm system into a dangerous one in a matter of hours. And this unpredictability is what defines the next stage of our investigation. Because understanding rivers that should not exist is not just about geography. It is about recognizing that stability in nature is never permanent. And in the next episode, we move deeper into the invisible mechanics that govern these transformations. The science behind the force, the structure behind the motion, and the reason why water, one of the most essential elements for life, can so easily become one of its most immediate threats. There is a fundamental problem with water. It does not reveal its internal structure to the human eye. A river can appear calm on the surface while containing violent motion beneath it. It can look shallow while hiding powerful downward pressure gradients. It can seem slow while internally accelerating through narrow subsurface channels. This disconnect between appearance and reality is where most misunderstandings begin. Because water is not a static object. It is a dynamic system governed by pressure, velocity, gravity, and resistance, all interacting simultaneously at every point in its flow. And when those forces shift even slightly, the entire system changes behavior. To understand how rivers become dangerous, we must first understand how motion in fluids actually works. At the most basic level, water moves because of gravity. Higher elevation water flows toward lower elevation areas. This creates a directional force known as potential energy conversion. But gravity alone does not determine how dangerous a river becomes. The real factor is how that energy is distributed. When water flows through open, wide channels, energy spreads evenly. The system remains relatively stable. Velocity increases gradually. Turbulence remains manageable. But when the channel narrows, everything changes. The same volume of water must pass through a smaller space. This creates acceleration, not because the water decides to move faster, but because physical constraints force it to. This principle is known in fluid dynamics as continuity of flow. When cross-sectional area decreases, velocity increases. And this is the first invisible transformation that turns ordinary rivers into dangerous systems. Because increased velocity does not just mean faster movement. It means increased force. Force that acts on everything in the water, including the human body. At higher speeds, water begins to exert pressure in multiple directions simultaneously. Forward pressure pushes objects downstream. Lateral turbulence destabilizes balance. Vertical pressure differences begin to form beneath the surface. And this is where the most dangerous phenomenon begins to appear. The downward pull effect. Often misinterpreted as suction, this is not a literal vacuum. Instead, it is the result of pressure differentials created by fast-moving water interacting with obstacles, drops, and submerged structures. When water flows over a sudden drop, such as a rock ledge or artificial barrier, it separates from the surface temporarily. Behind that separation point, low-pressure zones form. Water from surrounding areas rushes in to fill the gap, creating circular motion patterns. These patterns are not random chaos. They are structured loops. And within these loops, objects, including human bodies, can become trapped. This is one of the key mechanisms behind what are commonly called hydraulic traps. To the observer, the surface may look like a simple waterfall or rapid drop, but beneath it, the water is rotating in a continuous cycle, down, forward, up, and back again. Once inside this cycle, escape becomes extremely difficult because the system continuously repositions the body back into the same motion pattern. Even strong swimming effort often becomes ineffective because energy is being spent fighting the flow rather than breaking the loop. This is why many river accidents occur in seemingly shallow water. Depth is not the determining factor. Flow structure is. Another critical invisible force is turbulence. Turbulence is often misunderstood as random chaos. In reality, it is highly structured, irregular motion caused by disruptions in smooth flow. When water encounters obstacles, rocks, debris, narrow channels, it breaks into swirling eddies and vortices. Each vortex is a rotating system with its own internal momentum. In high-energy rivers, multiple vortices can form simultaneously, interacting with each other and creating complex flow networks beneath the surface. A person entering such a system is no longer dealing with a single current. They are interacting with multiple competing forces, some pushing forward, some pulling sideways, some dragging downward. This multidirectional pressure is what creates disorientation. The human brain relies heavily on stable reference points, up, down, left, right. But in turbulent water, those references collapse. Orientation becomes unreliable. And in that moment, survival decisions become significantly harder. One of the most dangerous misconceptions about rivers is that danger is visible. People expect to see white water, crashing waves, or obvious signs of chaos. But many of the most dangerous hydraulic systems occur in visually calm environments. This is because energy does not always manifest on the surface. In some cases, it is absorbed below. Subsurface flow can carry significantly more energy than surface motion suggests. This is especially true in deep channels where water is moving rapidly beneath a relatively smooth top layer. This creates what scientists refer to as laminar illusion, where flow appears stable but contains hidden turbulence beneath. These zones are particularly dangerous because they bypass human risk perception entirely. There is no visual warning, no audible cue, only sudden transition. Another key factor in river violence is pressure gradient instability. As water moves through uneven terrain, pressure differences develop between adjacent flow regions. These differences cause rapid acceleration of water between zones, leading to jet-like streams within the river system itself. These internal jets can exert localized force far beyond the average flow speed of the river. In practical terms, this means that one section of a river can behave like a calm stream, while another nearby section behaves like a high-speed hydraulic system. This inconsistency is what makes navigation unpredictable, and unpredictability is the foundation of risk. Historically, humans have attempted to control these forces through engineering. Dams, levees, and channel modifications are designed to regulate flow, reduce flooding, and stabilize water movement. But engineering does not eliminate energy. It redistributes it. In some cases, it concentrates it. Low-head dams are a prime example of this unintended consequence. By forcing water over a uniform drop, they create consistent recirculating currents beneath the surface. These currents are not random accidents. They are predictable physical outcomes of fluid behavior. Yet their predictability does not make them less dangerous. In fact, it often makes them more dangerous because their uniform appearance hides their internal complexity. From above, the water appears smooth and harmless. But below, it is continuously cycling through a closed energy loop. Downward pull, forward motion, upward return. Repeat indefinitely until external conditions change. This brings us to another crucial concept in fluid dynamics: system stability. A stable river system maintains consistent flow patterns over time. An unstable system fluctuates rapidly between different states. Most dangerous rivers exist in partially unstable states, where stability appears present, but underlying energy structures are constantly shifting. This creates a deceptive environment where conditions can change without visible warning. Rainfall upstream can suddenly increase flow volume. Snowmelt can accelerate seasonal discharge. Structural shifts in riverbeds can redirect entire currents overnight. Each of these factors alters the internal balance of the system. And when balance is disrupted, energy redistribution occurs instantly. What was once a manageable flow becomes a high-energy channel. And what was once safe becomes hazardous. The critical point to understand is that rivers do not become dangerous gradually in most cases. They transition, sometimes abruptly, sometimes invisibly. And this is what makes them so difficult to assess in real time. Because by the time danger is visually apparent, the system may already be fully active. In the next episode, we move from theory into impact, from invisible forces to real-world consequences, from fluid mechanics to human survival. And we begin to explore what happens when these systems are no longer observed, but entered. There is a moment in every river incident that defines everything that follows. It is not the moment of entry. It is not the moment of panic. It is the moment control is lost beneath the surface. Above water, survival feels active. Movement is visible. Direction is possible. Even in strong currents, the human body can attempt correction, adjusting position, reaching for stability, fighting against flow. But once the body passes below the surface, the environment changes completely. The rules no longer match human expectation. Sound disappears. Vision collapses. Orientation becomes unreliable. And most importantly, force becomes multidirectional. This is where rivers transition from powerful systems into enclosed mechanical environments that behave nothing like open water. To understand how people become trapped, we must first understand what happens beneath the surface layer. Because what appears as a simple body of flowing water is, in reality, a stacked system of interacting forces. The surface is only the visible boundary of a much deeper dynamic structure. Below it, water is constantly moving in multiple layers. Some layers flow forward rapidly, others circulate backward. Some move downward through pressure gradients. Others rise due to displacement and buoyancy shifts. A human body entering this system does not interact with a single current. It interacts with all of them at once. And that is where disorientation begins. One of the most critical mechanisms responsible for underwater entrapment is recirculating flow. In certain river conditions, water does not simply move downstream in a straight path. Instead, it forms looping structures where water cycles through a continuous rotation. Downward motion pulls objects beneath the surface. Forward motion carries them downstream. Upward motion brings them partially back toward the surface. And backward motion returns them to the original position. This creates a closed loop. From the outside, it may look like turbulence or churning water. From the inside, it behaves like a cycle with no exit point. The body is not stationary, but it is not escaping either. Each attempt to move forward is counteracted by the returning force of the loop. This is why many river entrapment cases show repetitive resurfacing before final submersion. It is not random struggle. It is repeated circulation within a structured hydraulic system. Another contributing factor is pressure imbalance beneath obstacles. When water flows under bridges, rocks, or submerged structures, it often accelerates into narrow gaps. This acceleration creates low-pressure zones on the downstream side. Water rushes in to fill these zones, producing backward suction-like motion. Although commonly described as suction, it is actually pressure equalization. But for a human body caught in this region, the effect is the same. Movement becomes restricted. Escape routes collapse. And the body is drawn repeatedly back into the high-energy zone. These conditions are especially dangerous in environments with hidden obstructions. Submerged rocks, fallen trees, and artificial structures create complex flow patterns that are invisible from above. Water may appear smooth on the surface, while forming violent rotational systems just beneath it. This is one of the most deceptive aspects of river physics. Visual calm does not equal physical safety. Another major factor in underwater entrapment is turbulence fragmentation. When high-speed water collides with irregular terrain, it does not flow as a single unified stream. It breaks into smaller, independent vortices. Each vortex rotates with its own internal energy, direction, and stability. A person entering such a system is no longer interacting with a single force, but multiple competing microsystems. Some vortices push downward. Some push sideways. Some accelerate forward. And others pull backward. This multi-vector environment creates what researchers describe as kinetic confusion. The body receives conflicting force inputs simultaneously, making coordinated movement extremely difficult. Even simple swimming motions become inefficient because each action is immediately counteracted by another force. This is why exhaustion occurs rapidly in strong river currents. It is not just physical effort. It is constant resistance from multiple directions. In addition to mechanical forces, there is also a psychological breakdown that occurs in submerged environments. The human brain relies heavily on spatial orientation. It expects gravity to behave consistently. It expects up to mean escape, and down to mean depth. But underwater in turbulent rivers, these references become unreliable. Air bubbles rise unpredictably. Light refracts through moving water layers. Sediment clouds obscure visibility, and rotation distorts directional awareness. As a result, the brain begins to misinterpret motion. What feels like upward movement may actually be lateral drift. What feels like progress may be circular motion within a hydraulic loop. This disconnect between perception and reality is one of the most dangerous aspects of river entrapment, because decisions are made based on incorrect spatial information. At the same time, oxygen limitation becomes a critical factor. Unlike open surface swimming, underwater entrapment in rivers often involves repeated submersion cycles. The body may briefly surface due to upward flow in a vortex, only to be pulled down again. These intermittent exposures to air create a false sense of opportunity. But they are part of the same cycle that prevents escape. Each resurfacing consumes energy. Each submersion increases disorientation. And over time, the body transitions from active resistance to passive movement within the flow system. Another important factor is sediment and debris interaction. Rivers often carry suspended particles, sand, silt, organic matter, and small debris. In high-energy conditions, this material becomes part of the flow structure. It reduces visibility further and increases frictional resistance against movement. In some cases, debris can physically obstruct escape routes or create entanglement hazards beneath the surface. Fallen branches, submerged vegetation, and artificial waste can all become secondary trapping mechanisms within an already dangerous system. When combined with hydraulic loops and turbulence, these factors create layered entrapment environments. This means that escape is not prevented by a single force, but by multiple overlapping systems working simultaneously. Historically, many river accidents have been misinterpreted as simple drowning incidents. But modern fluid analysis reveals a more complex reality. In many cases, victims are not simply overwhelmed by water. They are held within structured flow systems that continuously recycle their position within the same region of motion. This is why rescue operations in such environments are extremely challenging. Even trained professionals must account for unpredictable subsurface currents, hidden vortices, and structural hazards that cannot be fully observed from above. Approaching a trapped zone can place rescuers into the same hydraulic systems, creating secondary risk. This is why certain river rescue situations are considered among the most dangerous in emergency response work. Another overlooked aspect is time compression. From an external perspective, river incidents may appear to unfold over several minutes. But from the perspective of the individual within the system, conditions change in seconds. Initial entry is often followed by immediate loss of footing. Within moments, orientation becomes unstable. Shortly after, repeated submersion cycles begin. And once these cycles stabilize, the system enters a sustained entrapment phase. This rapid progression leaves very little margin for correction. Unlike other environmental hazards, rivers do not provide gradual escalation in many cases. They transition quickly from stable to unstable states. And once that transition occurs, reversal is difficult without external intervention. As we move forward in this investigation, we begin to shift from mechanical explanation to human impact. because understanding how these systems function is only part of the story. The other part is understanding what happens when humans encounter them directly. Not in theory, but in reality. And in the next episode, we examine the structural failures, engineering interventions, and environmental conditions that amplify these dangers. Even further, human beings did not only learn to fear rivers, they learned to reshape them. Across history, civilizations have tried to control water, not by avoiding it, but by forcing it into predictable paths. Dams, canals, levees, spillways, diversion channels, each structure designed with a single promise: control the flow, reduce the risk, protect human life. But water does not surrender to design. It responds to it. And in many cases, it responds in ways that were never intended. What begins as protection can transform into amplification. What begins as stability can become concentrated danger. And in certain engineered environments, rivers do not become safer. They become more violent. This is the hidden paradox of hydraulic engineering. Because water is not eliminated by structures, it is redirected. And when energy is redirected into confined spaces, it does not disappear. It intensifies. One of the most misunderstood engineering structures in river systems is the Lowhead Dam. From a distance, it appears harmless. A simple, uniform drop where water flows smoothly over a horizontal barrier. The surface looks controlled, even peaceful. There is often no dramatic waterfall, no visible chaos, no obvious sign of danger. But beneath that uniform flow lies one of the most lethal hydraulic environments created by human design. When water passes over a Lowhead Dam, it drops abruptly on the downstream side. This sudden change in elevation causes the flow to separate from the surface. Behind this separation point, water begins to recirculate. A continuous loop forms beneath the surface. Water moves downward, then forward, then upward, and back again toward the dam face. This creates a hydraulic recirculation zone that traps anything entering it. From the outside, it looks like smooth, harmless flow. From the inside, it behaves like a conveyor system with no exit. Objects entering this zone are repeatedly pulled back toward the dam structure, not by suction, but by continuous rotational energy within the flow system. This is why Lowhead dams are often referred to by water safety experts as drowning machines. Not because they are unpredictable, but because they are consistently dangerous in the same predictable way. The hazard lies in perception. Most people do not recognize the structure as dangerous because it does not visually match the idea of a waterfall or rapid current. Instead, it appears uniform, controlled, engineered, and that visual consistency creates a false sense of safety. But in fluid dynamics, uniform appearance does not guarantee uniform behavior. In fact, uniform surfaces often hide complex subsurface motion. The energy passing over a Lowhead dam does not dissipate. It reorganizes into a stable, self-sustaining vortex system. Once formed, this system can persist as long as water flow continues. And within this system, escape becomes extremely difficult. Even strong swimmers struggle because the recirculating force continuously returns them to the base of the structure. Attempts to move away are counteracted by returning flow vectors beneath the surface. This creates a closed-loop environment with no natural exit point. In many documented cases, rescue attempts have failed not because of lack of effort, but because rescuers themselves become caught in the same hydraulic cycle. This introduces a secondary danger, cascading entrapment. One victim becomes multiple victims within the same flow system. And this is not limited to low-head dams. Similar effects occur in poorly designed spillways, irrigation channels, and flood control structures. Anywhere water is forced to drop suddenly and reattach to a downstream surface, recirculation zones can form. The key factor is not the size of the structure. It is the geometry of flow separation. Another major engineering risk in river systems is channelization. When natural rivers are modified into straight, confined channels, water loses its natural ability to dissipate energy across wide areas. Instead, it becomes concentrated. Velocity increases, turbulence intensifies, and flow becomes more uniform, but also more forceful. This creates high-speed hydraulic corridors that can behave unpredictably during flood conditions. In natural rivers, bends and irregularities slow down flow and distribute energy. In engineered channels, that variability is often removed. The result is a system that is more efficient at moving water, but less forgiving during high-energy events. During heavy rainfall or snowmelt, these channels can rapidly transition from controlled drainage systems into high-velocity water highways. And because they are often integrated into urban environments, the risk extends directly into populated areas. Another overlooked engineering hazard is sediment buildup. When water flow is modified, sediment transport patterns change. In some cases, sediment accumulates upstream of structures. In others, it erodes downstream channels, deepening flow paths and altering hydraulic behavior. This can gradually reshape the river system over time, creating new flow dynamics that were not part of the original design. What makes this especially dangerous is that these changes are often invisible on short timescales. A structure may appear stable for years, but internally, flow patterns are continuously evolving until a threshold is reached, and then the system behaves differently. Sometimes abruptly, sometimes catastrophically. This delayed response is one of the most challenging aspects of hydraulic engineering, because systems that appear stable can still be undergoing internal energy redistribution. One of the most critical failures in water engineering occurs when multiple forces converge. For example, a controlled channel meets a flood surge. A low-head dam meets high-volume discharge. A spillway meets debris-laden flow. In these situations, engineered stability collides with natural variability, and the result is often amplification of hydraulic intensity. Flow speeds increase beyond design expectations. Recirculation zones expand. Turbulence becomes more chaotic, and previously predictable systems enter unstable regimes. This is where engineering limits are exposed, not because design is inherently flawed, but because natural systems operate with variables that cannot always be fully controlled. Another important aspect of engineering-related river danger is maintenance neglect. Even well-designed structures degrade over time. Concrete surfaces erode. Flow edges become irregular. Obstructions accumulate. And small geometric changes can significantly alter hydraulic behavior. In fluid systems, small changes can produce large effects. This is known as sensitivity to initial conditions. A minor shift in flow geometry can transform a stable system into an unstable one. A slight obstruction can create a new vortex. A small drop in elevation can generate a recirculation zone. And over time, these small changes accumulate until the system behaves in ways that differ from its original design parameters. This is why continuous monitoring is essential in hydraulic infrastructure, because water systems are not static. They evolve, even when the structures around them do not. Historically, Many river-related engineering disasters have been misunderstood as natural accidents. But modern analysis often reveals a combination of design limitation, environmental variability, and structural evolution. In many cases, the danger is not a single failure point. It is a chain of small interactions that collectively destabilize flow behavior. This complexity is what makes water engineering one of the most challenging fields in civil design. Because unlike static structures, rivers are dynamic systems that respond continuously to external and internal changes. And as human development expands into more river-adjacent environments, these interactions become more frequent. Bridges span faster-flowing channels. Cities expand near flood-prone waterways. Infrastructure modifies natural drainage systems. And each intervention adds a new layer of complexity to the system. In the next stage of this investigation, we move away from engineered systems and return to nature at its most unpredictable. Because even without human intervention, rivers possess the ability to shift, collapse, and transform in ways that defy expectation. And when nature reasserts control, the consequences can extend far beyond infrastructure. They extend into survival itself. There is a point in every river system where prediction fails. Not because science is incomplete, but because scale changes everything. A river that behaves calmly for months can transform within hours. A stable channel can become a violent torrent. A shallow flow can turn into a destructive force capable of reshaping entire landscapes. This is the moment when nature breaks control. And when it happens, it does not ask for permission. Rivers are often described as stable systems because they follow gravitational logic. Water flows downhill. It follows the path of least resistance. It responds to terrain. But this simplicity hides a deeper truth. Rivers are not stable systems. They are dynamic equilibrium systems. This means they constantly adjust themselves in response to changing conditions: rainfall, temperature, upstream discharge, sediment load, and terrain shifts. Most of the time, these adjustments are gradual. But under certain conditions, the system reaches a threshold. And beyond that threshold, change becomes rapid. This is the point of transformation. One of the most powerful triggers of river transformation is extreme rainfall. When rainfall exceeds the absorption capacity of soil and tributaries, water begins to accumulate rapidly in upstream regions. This accumulated water does not remain static. It converges into river channels, increasing volume dramatically. As volume increases, velocity responds. Not linearly, but exponentially in confined environments. This is where calm rivers begin to change character. The surface becomes unstable. Flow patterns begin to reorganize. And energy distribution shifts from uniform to concentrated. Another major factor is snowmelt in mountainous regions. During seasonal warming, accumulated snow and ice release large volumes of water into river systems. This process can significantly increase discharge rates over short periods. When combined with rainfall, the effect is amplified. Rivers that normally operate within stable limits suddenly experience peak flow conditions far beyond their baseline state. But water volume alone does not define danger. The real transformation occurs in flow behavior. As discharge increases, rivers begin to interact more aggressively with their boundaries. Riverbanks become erosion zones. Sediment is displaced. Channels deepen or widen depending on resistance patterns. And as geometry changes, flow dynamics shift again. This creates a feedback loop. More water leads to more erosion. More erosion changes flow paths. Changed flow paths alter velocity distribution. and altered velocity redistributes energy again. This is a self-reinforcing system. Once initiated, it can accelerate rapidly. In extreme cases, rivers can change course entirely. This process is known as avulsion. It occurs when a river abandons its existing channel and forms a new path through the landscape. From a geological perspective, avulsion is a natural part of river evolution. From a human perspective, it can be catastrophic. Entire settlements, agricultural regions, and infrastructure can become disconnected from water sources or submerged under new flow paths. Another critical phenomenon during extreme river events is flash flooding. Unlike gradual flooding, flash floods occur when water accumulates and releases rapidly over a short time scale. These events are often triggered by intense rainfall in localized areas. Because the water has little time to disperse, it moves as a concentrated surge. This surge can travel through river channel with extreme speed. And because it often carries debris, sediment, and erosion material, its destructive capacity increases significantly. In flash flood conditions, rivers lose their typical structure. They become moving walls of water, reshaping everything in their path. Bridges can be overwhelmed, roadways submerged, natural barriers eroded. But what makes these events especially dangerous is their unpredictability. They can occur in regions that appear stable moments before. Clear skies upstream do not always reflect conditions downstream. This disconnect between perception and reality is one of the most dangerous aspects of river systems during extreme events. Another overlooked factor in river transformation is subsurface saturation. When soil becomes fully saturated, its ability to absorb additional water disappears. At this point, all incoming water contributes directly to surface flow. This accelerates runoff into river channels, increasing pressure within the system. Combined with erosion, this can destabilize riverbanks and trigger sudden collapses. These collapses introduce additional sediment into the flow, further altering hydraulic behavior. The river becomes heavier, faster, and more unpredictable. But perhaps the most visually deceptive stage of river transformation is the transition phase. This is the period when a river is shifting from stable to unstable conditions. During this phase, surface appearance may not fully reflect internal energy changes. Water can still appear navigable. Flow can still seem controlled. But beneath the surface, velocity gradients are increasing. Pressure zones are forming. And turbulence is expanding. This mismatch between appearance and internal behavior is what leads to many misjudgments in river safety. Because humans tend to assess risk based on surface observation. But rivers do not operate at the surface alone. They operate in 3 dimensions. And during transformation events, much of the energy is distributed below visible layers. As flow intensity increases, rivers also begin to interact more aggressively with obstacles. Large debris such as trees, rocks, and man-made objects become mobile within the system. These objects are not passive. They become part of the flow dynamics. Carried by current, they can impact structures, alter flow paths, and create localized turbulent zones. In some cases, debris accumulation can form temporary blockages. These blockages store energy upstream, and when they eventually fail, they release that energy suddenly downstream. This creates secondary surge waves within the river system. These surges can be just as dangerous as the original flood event. In mountainous regions, river transformation can also trigger landslides. As banks erode, slopes become unstable. Combined with saturation, this instability can lead to mass movement of earth into river channels. This not only increases water displacement, but also adds solid material into the flow. The river becomes a hybrid system of water and debris. Its behavior becomes even less predictable. Another important aspect of nature-driven river instability is temporal variability. Unlike engineered systems that attempt to maintain consistent flow, natural rivers operate on fluctuating cycles. Daily, seasonal, and climatic variations all influence behavior. During transition periods between seasons, instability peaks. This is when rivers are most likely to shift behavior unexpectedly. And because these shifts are driven by multiple interacting variables, prediction becomes increasingly difficult. Modern hydrological systems attempt to model these changes using satellite data, weather forecasting, and historical patterns. But even with advanced tools, uncertainty remains. Because river systems are not isolated. They are connected to atmospheric systems, geological structures, and ecological cycles. This interconnectedness means that small changes in one domain can produce large effects in another. A rainfall event in one region can influence river behavior hundreds of kilometers downstream. A temperature shift can alter snowmelt timing. A geological shift can redirect entire flow networks. In essence, rivers are part of a larger environmental system that is constantly in motion. And when enough variables align, transformation becomes inevitable. In the final stage of this episode's focus, we return to the central theme. Nature does not break control because it is unstable. It breaks control because it is adaptive. An adaptation under extreme conditions can produce outcomes that exceed human expectation. In the next episode, we move from environmental transformation to human experience within these systems. Because understanding how rivers change is only part of the story. The next step is understanding what happens when people are directly caught inside those changes. When survival is no longer theoretical, but immediate, there is a strange contradiction at the center of every river survival story. On one side, the physics is absolute. Water follows measurable laws. Flow has structure. Forces can be calculated, modeled, and predicted with increasing accuracy. On the other side, human survival often appears to defy those same systems. People escape situations that should, by every mechanical expectation, be unsurvivable. Not because the laws of physics break, but because within those laws, there are rare moments where timing, position, and environmental fluctuation align just long enough to allow escape. These are not miracles. They are edge cases in a highly complex system. And they are the only reason survival is sometimes possible in violent river environments. To understand how escape happens, we must first understand what survival actually means in a hydraulic system. Survival in river currents is not about strength. It is about interaction with flow structure. Because once a person enters moving water, they are no longer operating independently. They become part of the system. Their body is influenced by velocity gradients, pressure zones, turbulence fields, and rotational currents. Every movement is either amplified or resisted by these forces. This is why conventional assumptions about swimming ability often fail in extreme river conditions. A strong swimmer in still water is not equivalent to a strong swimmer in a dynamic flow system, because the environment itself is actively changing the outcome of every movement. Yet despite this, there are documented cases where individuals have escaped violent currents. When examined closely, these cases reveal consistent patterns, not of luck alone, but of physics interacting with human response. One of the most critical survival mechanisms is energy conservation during flow interaction. In high-velocity water, resistance-based swimming, Fighting directly against the current rapidly leads to exhaustion. The body spends energy-opposing forces that are significantly larger than muscular output can counteract. This is why many survival guides emphasize directional adaptation rather than opposition. But in real incidents, survival often occurs before conscious strategy can even be formed. It begins with instinctive body positioning. In turbulent water, horizontal orientation reduces drag compared to vertical struggle. A body aligned with flow direction experiences less resistance than one fighting perpendicular to it. This reduces energy expenditure and increases the chance of reaching calmer zones. Calmer zones are not random. They are often located near river edges, behind obstacles, or in recirculation boundaries where velocity decreases. These regions act as transition areas between high-energy flow and slower boundary layers. In many survival cases, escape occurs when individuals are unintentionally guided into these zones by turbulence patterns. Another key factor is buoyancy timing. Human bodies are naturally buoyant to a degree, but this buoyancy interacts with flow velocity. In recirculating currents, buoyancy can temporarily lift a person toward the surface during upward flow phases. These brief resurfacing moments are critical. They provide short windows for air intake, orientation, and directional adjustment. However, these windows are unstable and unpredictable. They are governed by vortex cycles that may last only seconds. Survivors often report feeling carried upward unexpectedly before being pulled back down. This is not random behavior. It is structured rotational flow. In some cases, escape occurs when individuals manage to move laterally during these upward phases, exiting the primary circulation zone. Lateral movement is often more effective than forward movement in hydraulic systems, because escaping a vortex is not about overpowering it. It is about leaving its boundary. Another documented survival factor is debris interaction. Although debris increases danger in most cases, it can also create accidental escape pathways. Floating objects such as logs or branches can alter local flow velocity, creating temporary gaps in circulation zones. If a person is carried alongside or above such objects, they may be lifted into slightly different flow regions with reduced rotational force. These transitions are rare, but they are physically consistent with fluid behavior. There is also the phenomenon of boundary layer drift. Along river edges, water velocity decreases due to friction with terrain. This creates a gradient between fast central flow and slower outer flow. Survivors who reach this boundary layer often experience a reduction in force intensity. From there, gradual movement toward shore becomes more feasible. However, reaching this zone requires either deliberate movement or accidental displacement by turbulence. In many survival accounts, individuals do not consciously navigate to safety. They are repositioned by flow dynamics into marginally safer areas. This highlights a critical truth. Survival in rivers is often not a result of control. It is a result of transition. Another important aspect is time-dependent fatigue reduction. In extreme water conditions, human performance deteriorates rapidly. Muscle fatigue, panic response, and oxygen depletion combine to reduce coordination. However, once individuals cease high-resistance movement and shift into passive floating states, energy consumption decreases. This can extend survival windows long enough for environmental changes to occur. For example, a shift in current direction, a reduction in turbulence intensity, or a change in flow obstruction alignment. These environmental shifts may create escape opportunities that did not exist seconds earlier. In this sense, survival is not static. It is dynamic interaction with evolving conditions. Some of the most well-documented survival cases involve accidental entry into hydraulic cycles, followed by unexpected exit points. For example, a person caught in a recirculating zone may be repeatedly cycled through the same motion pattern for several rotations. Then, due to a minor change in flow structure, such as debris displacement or pressure fluctuation, the loop breaks. At that moment, the system transitions from closed circulation to open flow. If the individual is positioned correctly during this transition, they may be ejected from the hazard zone. These ejection events are rare, but they follow consistent physical principles. They occur when energy redistribution disrupts stable vortex formation. Another factor influencing survival is spatial awareness under stress. Although turbulence significantly impairs orientation, some individuals retain partial awareness of surface direction and shoreline position. This can influence micro-movements that increase the probability of reaching boundary zones. However, even this awareness is often secondary to environmental forcing. Because in high-energy rivers, movement is dominated more by flow than by intention. Rescue operations in such environments further highlight the complexity of survival. External intervention often depends on timing, positioning, and accessibility of flow zones. Rescuers must avoid entering the same hydraulic system that trapped the victim. This limits direct intervention and often requires indirect extraction methods such as ropes, mechanical systems, or downstream recovery points. In some cases, rescue success depends on environmental stabilization rather than direct retrieval. A reduction in flow intensity, a shift in debris alignment, or a change in water level can create safer conditions for extraction. This reinforces the idea that survival and rescue are deeply tied to environmental state changes, not just human action. Another critical observation from survivor reports is the perception of time distortion. Many individuals describe time slowing or fragmenting during high-stress river incidents. This is a neurological response to extreme sensory overload. The brain processes rapid environmental changes by altering temporal perception. While this does not change physical reality, it affects decision-making and reaction timing. In some cases, this altered perception may allow for micro-adjustments that improve survival probability. But it can also lead to misjudgment of distance, force, and direction. Ultimately, survival in violent river systems is not determined by a single factor. It is the result of overlapping conditions: flow structure, body positioning, energy conservation, environmental transitions, random hydrodynamic shifts. When these align in rare configurations, escape becomes possible, but not guaranteed. In the next episode, we move beyond individual survival stories. We examine the rivers themselves, the most dangerous systems on Earth, the locations where these forces are not occasional, but constant, and where survival is not an exception. It is a statistical anomaly. Danger in rivers is not evenly distributed across the planet. It concentrates in specific geographic conditions, where terrain, climate, and water volume combine in ways that push flow dynamics toward extremes. These are not ordinary rivers. They are systems operating near the upper limits of hydraulic energy for their environment. And across continents, they share one defining trait: they do not behave predictably. From tropical rainforests to high-altitude canyons, from glacial melt zones to engineered waterways inside cities, certain rivers consistently demonstrate conditions that amplify flow instability. Not because they are malicious, but because their environments continuously feed them energy faster than it can be dissipated. To understand why these rivers are so dangerous, we must examine the conditions that create them. Because geography is not just a backdrop. It is an active force shaping water behavior. One of the most extreme river environments exists in steep mountainous regions. Here, gravity dominates the system. Water descends rapidly through narrow channels carved into rock over thousands of years. But unlike flat river systems, these channels do not allow gradual energy dispersion. Instead, water is forced into confined paths with sudden drops, sharp bends, and irregular boundaries. Each of these features increases turbulence, and turbulence increases unpredictability. In some mountainous rivers, flow velocity can change dramatically over short distances. A calm stretch can immediately transition into high-speed rapids without visible warning. This is because energy is not distributed evenly. It is segmented by terrain. Another high-risk environment is glacier-fed river systems. In these regions, meltwater enters rivers in large, seasonal pulses. During warmer periods, ice melts rapidly, increasing discharge volume. But this water carries with it suspended sediment, rock particles, and debris from glacial erosion. This mixture significantly alters flow density and behavior. Heavier water interacts differently with riverbeds, increasing erosion potential and changing channel geometry over time. As a result, glacier-fed rivers often exhibit rapidly shifting flow patterns that evolve within a single season. In tropical regions, another dangerous category emerges: flood-driven river systems. These rivers are heavily influenced by rainfall variability. During dry periods, they may appear shallow and manageable. But during monsoon or storm events, they transform rapidly into high-volume systems. Because tropical rainfall can be extremely concentrated in time and location, rivers in these regions often experience sudden surges in discharge. This leads to flash flood conditions that can overwhelm natural and artificial boundaries alike. What makes these rivers particularly dangerous is the speed of transition. Conditions can shift from safe to extreme in a matter of hours. In some cases, minutes. Urban river systems present a different kind of hazard. These rivers are often modified by human infrastructure. Channelization, damming, drainage systems, and flood control structures alter natural flow patterns. While the goal is stability, the result is often increased flow concentration. Water that would normally spread across floodplains is instead confined to engineered pathways. This increases velocity and reduces natural dissipation zones. In extreme weather events, these systems can become overwhelmed, leading to rapid urban flooding. But even in non-flood conditions, engineered rivers can contain hidden hydraulic hazards created by structural modifications. Among the most dangerous urban-adjacent systems are rivers with low-head dams and diversion structures. These areas often create recirculating hydraulic zones that are not easily visible from the surface. In mountainous canyon systems, another hazard appears: confined acceleration zones. Here, rivers are forced through narrow rock corridors. As the channel width decreases, velocity increases. This creates high-energy flow systems, where escape options are limited by geography itself. These environments are particularly dangerous because there is little margin for lateral movement. The river occupies nearly the entire available space. One of the most well-known examples of extreme river behavior occurs in steep canyon rapids. These systems combine vertical drop, confined geometry, and high discharge volume. The result is a multi-layered turbulence field where water behaves in highly complex ways. Surface flow may appear chaotic, but subsurface motion can be even more intense. Rotational vortices, downward plunges, and lateral shear zones interact simultaneously. In such systems, navigation becomes extremely difficult even for experienced operators. Another important factor in river danger is seasonal variability. Many of the world's most dangerous rivers are not consistently extreme. They fluctuate between stable and unstable states, depending on environmental conditions. Snowmelt, rainfall, and temperature shifts all influence discharge levels. This means that a river's danger profile is not fixed. It changes throughout the year. In some regions, the most dangerous conditions occur during transitional seasons, when multiple variables overlap. For example, late spring may combine snowmelt with rainfall, creating peak discharge conditions. In other regions, late summer storms can suddenly activate normally stable river systems. This variability makes long-term risk assessment extremely complex, because a river that appears safe in one month may behave entirely differently in another. Another category of dangerous rivers includes those influenced by geological instability. In tectonically active regions, river channels may be altered by earthquakes, landslides, or gradual uplift. These geological changes can redirect flow paths or introduce new obstructions into the system. When this occurs, rivers may carve entirely new channels through landscapes. This process can be slow or sudden, depending on the scale of the geological event. But in both cases, it introduces uncertainty into previously stable systems. Sediment-heavy rivers also present unique risks. When rivers carry large amounts of suspended material, their density and flow characteristics change. Sediment can increase friction along riverbeds, alter flow velocity distribution, and create shifting underwater structures. These structures are not fixed. They evolve as sediment is deposited and eroded over time. This creates a constantly changing underwater environment that cannot be fully mapped at any single moment. Another important factor is confluence zones, areas where multiple rivers merge. At these points, different flow systems collide. Each river may carry different velocity, sediment load, and temperature. When they meet, the interaction can produce complex turbulence fields. Flow separation, eddy formation, and shear zones often develop at these intersections. These are not necessarily dangerous in all conditions, but under high discharge events, they can become highly unstable. In coastal river systems, tidal influence adds another layer of complexity. Rivers that meet ocean or seas experience bidirectional flow dynamics. Incoming tides push water upstream, while river discharge pushes outward. This interaction can create standing wave systems, reverse currents, and fluctuating flow boundaries. These environments are highly dynamic and change multiple times within a single day. What emerges from all these examples is a consistent pattern. River danger is not defined by a single factor. It is defined by convergence, where multiple environmental forces interact simultaneously. Gravity, terrain, climate, sediment, and human intervention all combine to shape behavior. And when these forces align in extreme configuration, rivers reach their most dangerous states. Importantly, these systems are not static threats. They are evolving systems. A river that is dangerous today may stabilize tomorrow, and a stable river may become dangerous without warning. This variability is what makes them difficult to fully categorize, because they do not remain in one condition long enough to be permanently defined. In the next episode, we move beyond geography and into the future. Because the behavior of rivers is no longer influenced only by natural forces. It is increasingly shaped by climate change, environmental disruption, and global hydrological shifts. And these changes are rewriting the rules of river behavior itself. For most of human history, rivers changed slowly. Their behavior was shaped by predictable cycles, seasonal rainfall, gradual snowmelt, and long-term geological processes. Communities adapted to these rhythms over generations. Floodplains were mapped. River patterns were learned. Risk became something that could be anticipated. But that stability is no longer guaranteed. Because today, the systems that govern river behavior are being reshaped at a global scale. Not by geography alone, but by climate. Climate change does not simply make rivers bigger or faster. It alters the timing, intensity, and distribution of water across entire hydrological networks. And when those variables shift simultaneously, river systems begin to behave in ways that historical models struggle to predict. One of the most significant changes is the increase in extreme precipitation events. Instead of steady rainfall distributed over long periods, many regions now experience short bursts of intense downpours. These concentrated events overwhelm natural absorption systems. Soil saturates quickly, runoff increases dramatically, and rivers receive sudden surges of water far beyond their normal capacity. This is where river systems begin to transition into high-energy states more frequently than before. Because when input increases suddenly, flow systems must respond immediately. And that response is rarely gradual. It is structural. Another major factor is rising global temperature. Warmer air holds more moisture, which increases the potential energy available for precipitation events. This does not guarantee constant rainfall, but it increases the intensity of rainfall when it occurs. As a result, storms become less predictable and more concentrated. When these storms interact with river basins, discharge levels can spike rapidly. In mountainous regions, climate change is accelerating glacier melt. Glaciers act as long-term water reservoirs, releasing water gradually over time. But as temperatures rise, this release becomes uneven. Instead of steady seasonal flow, many glacier-fed rivers now experience unstable discharge patterns. Periods of extreme flow are followed by reduced flow, creating variability that destabilizes river systems. This variability affects not only water volume, but also sediment transport. As glaciers retreat, they expose loose geological material. This material enters river systems, increasing sediment load and altering flow density. Sediment-rich water behaves differently from clear water. It has greater mass, higher friction, and more complex interaction with riverbeds. This changes erosion patterns and reshapes channels more rapidly than in stable conditions. Another critical consequence of climate change is the increase in rapid snowmelt events. Warmer temperatures can trigger sudden melting of snowpack in mountainous regions. When this happens, large volumes of water enter river systems over short periods. If combined with rainfall, the effect is amplified further. These overlapping inputs create peak discharge events that can overwhelm natural channels. In lowland regions, climate change is increasing the frequency of floodplain activation. Floodplains are natural overflow zones designed to absorb excess water. But when extreme events become more frequent, these systems can be activated repeatedly within short time intervals. This reduces recovery time for ecosystems and increases long-term instability in river behavior. Urban environments are also increasingly affected. Cities built near rivers often rely on historical flow data to design infrastructure. But as climate patterns shift, historical data becomes less reliable. Drainage systems, levees, and flood defenses may no longer align with current flow conditions. This mismatch increases vulnerability during extreme events. Another emerging factor is the increase in compound weather events. Instead of a single trigger, such as rainfall or snowmelt, multiple factors now occur simultaneously. For example, heavy rainfall combined with saturated soil and upstream snowmelt can create amplified river responses. These compound events are particularly dangerous because they exceed the predictive capacity of traditional models. They are not just larger versions of past floods. They are structurally different events. Climate change also affects river timing. Seasonal patterns that once guided river behavior are shifting. Snowmelt may occur earlier in the year. Rainfall seasons may shift in duration or intensity. This temporal instability disrupts long-established ecological and hydrological cycles. As timing shifts, so does risk distribution. Flood events may occur in periods previously considered low risk. This increases uncertainty for both natural ecosystems and human settlements. Another important aspect is drought-flood alternation. Some regions are experiencing longer dry periods followed by intense flooding. Dry soil becomes less absorbent over time. When heavy rainfall eventually occurs, water runs off rapidly instead of being absorbed. This increases flash flood potential. So the system becomes more volatile at both extremes. Dry conditions become drier. Wet conditions become more extreme. This dual amplification increases overall river system instability. Climate change also influences coastal river systems. Rising sea levels affect the interaction between rivers and oceans. As sea levels rise, river discharge becomes more difficult, creating backflow conditions during high tides or storm surges. This can slow river drainage and increase upstream flooding risk. In some cases, saltwater intrusion can alter freshwater ecosystems and change flow dynamics near river mouths. Another critical effect is increased wildfire rainfall interaction in some regions. Wildfires remove vegetation that normally stabilizes soil. When heavy rainfall follows a fire event, soil erosion increases dramatically. This leads to debris flows entering river systems. These debris flows can transform clear rivers into dense, fast-moving mixtures of water, ash, and sediment. The hydraulic behavior of such systems is significantly more unpredictable than normal flow conditions. As all these factors combine, one pattern becomes clear. Climate change does not create a single type of river hazard. It multiplies existing ones. It increases frequency. It increases intensity. And it increases unpredictability. This means that rivers are not becoming uniformly more dangerous. They are becoming more variable. And variability is one of the most difficult factors to manage in any dynamic system, because it reduces the reliability of past experience. What was once a stable reference point may no longer apply. This is particularly important for regions that rely on historical flood records for planning. If baseline conditions shift, then risk models must also shift. Otherwise, systems designed for one era may fail under new conditions. But perhaps the most significant change brought by climate-driven river behavior is psychological. Human perception of safety is often based on repetition. If a river behaves consistently for years, it is perceived as stable. But when variability increases, that perception becomes unreliable. This creates a gap between expectation and reality. And that gap is where risk increases, because decisions are still being made based on outdated assumptions. In this way, climate change does not just alter rivers. It alters how humans interpret them. And this reinterpretation is still ongoing. In the next and final episode, we move beyond environmental change and into reflection. Because after understanding the physics, geography, engineering, and climate forces behind violent rivers, one question remains. What does it mean for humanity to live alongside a system that cannot be fully controlled? At the edge of every river, there is a question that never fully disappears. Not about where the water is going, but about what happens when we try to live beside something we cannot fully control. For thousands of years, human civilization has been built alongside rivers, not by accident but by necessity. Rivers provide water for agriculture, transportation routes, fertile soil, and access to trade. Entire cities exist because rivers exist. And yet the same systems that sustain life are also capable of taking it away with no warning. This duality is not new. What is changing is scale. Because as human civilization expands, so does its interaction with river systems. Infrastructure grows closer to flood zones. Populations increase along riverbanks. Engineering attempts to stabilize flow become more complex and more widespread. But rivers are not static environments. They are adaptive systems. And adaptation does not always align with human expectation. Looking into the future, one of the most significant challenges is increasing hydrological volatility. As climate systems shift, river behavior becomes less predictable across time. Historical stability is no longer a guarantee of future stability. This creates a fundamental problem for long-term planning. Because most infrastructure is built on the assumption that past patterns will continue. Bridges are designed using historical flood data. Cities are planned around known river boundaries. Agricultural systems rely on predictable seasonal flow. But when those patterns change, every assumption must be reevaluated. This is not a sudden collapse. It is a gradual mismatch between design and reality. And that mismatch grows over time. One of the most important shifts in the future of river systems is the increase in extreme variability. Instead of moderate, predictable flow conditions, rivers are increasingly experiencing alternating extremes. Long dry periods followed by sudden floods. Stable flow interrupted by rapid surges. Low energy states transitioning quickly into high energy states. This variability is difficult to manage because it reduces the reliability of long-term prediction models. Even advanced simulation systems struggle when baseline conditions shift frequently. Another major factor shaping the future of rivers is urban expansion. As cities grow, they encroach further into floodplains and natural drainage zones. This increases the interaction between engineered environments and natural water systems. Stormwater systems, drainage networks, and river channels become interconnected in complex ways. When extreme events occur, these interconnected systems can amplify flooding rather than reduce it. Water that would normally disperse across natural terrain is instead directed through constrained urban pathways. This increases flow speed and pressure in localized areas. Another emerging issue is infrastructure aging. Many river control systems, dams, levees, and channels were built decades ago based on environmental conditions that no longer match current realities. As these systems age, their ability to manage extreme events decreases. Small structural changes over time, erosion, sediment buildup, material fatigue, can alter hydraulic behavior in significant ways. And because these changes are gradual, they are often not detected until a threshold is reached. When that threshold is crossed, system behavior can change abruptly. The future also brings increased complexity in sediment transport. As rainfall patterns shift and extreme weather events become more common, rivers will carry more variable sediment loads. This affects channel stability, water clarity and flow dynamics. In some regions, increased sediment deposition may raise riverbeds over time, increasing flood risk. In others, accelerated erosion may deepen channels and destabilize banks. These processes are slow but cumulative, and over decades, they reshape entire landscapes. One of the most important long-term concerns is the interaction between rivers and rising sea levels. Coastal rivers are particularly sensitive to this change. As sea levels rise, the boundary between river and ocean shifts inland. This creates backflow conditions where tidal forces push against river discharge. During storm events, this interaction can become even more intense, increasing upstream flooding risk. Saltwater intrusion can also alter freshwater ecosystems and change the physical behavior of river mouths. Another factor shaping the future is increased frequency of compound disasters. Instead of isolated events, multiple environmental stressors now occur together. For example, heavy rainfall combined with saturated soil, snowmelt combined with upstream storm systems, storm surge combined with river discharge. These overlapping events create amplified hydrological responses that exceed normal design expectations. This makes risk management significantly more complex, because it is no longer about preparing for one event at a time. It is about preparing for interactions between events. Another important dimension of the future is technological monitoring. Satellite imaging, AI-based prediction systems, and real-time hydrological sensors are improving our ability to track river behavior. These systems allow for faster response times and more detailed analysis of flow conditions. However, they do not eliminate uncertainty. They reduce delay in detection, but not variability in behavior. Because rivers remain complex systems with many interacting variables, one of the most significant challenges moving forward is the gap between prediction and action. Even when systems detect potential hazards, response depends on infrastructure, governance, and human decision-making. And those systems often operate on slower timescales than environmental change. This creates a critical timing mismatch. In future scenarios, the speed of environmental transformation may exceed the speed of human response in certain conditions. This is not a failure of technology. It is a limitation of synchronization between natural and human systems. At a deeper level, the future of rivers also raises philosophical questions. Because rivers are not just physical systems. They are foundational elements of civilization. They shape borders, economies, ecosystems, and cultural development. And yet they remain fundamentally uncontrollable at full scale. We can guide them. We can modify them. We can partially predict them. But we cannot fully stabilize them. This leads to a central realization. Human civilization does not exist apart from rivers. It exists within their influence. And that influence is not static. It evolves. As we move forward, the relationship between humans and rivers will increasingly depend on adaptation rather than control. This means designing systems that can respond to variability rather than eliminate it. It means accepting that uncertainty is not an anomaly. It is a permanent condition. And perhaps most importantly, it means recognizing that safety is not defined by the absence of danger, but by the ability to respond when conditions change. In the end, rivers represent more than water flow. They represent a larger principle about natural systems. They are continuous, adaptive, and indifferent to expectation. And within that indifference lies both risk and balance. Because the same forces that create danger also sustain life. Agriculture depends on flood cycles. Ecosystems depend on seasonal variation. Civilization depends on water movement. So the question is not whether rivers are dangerous or safe. The question is how well we understand the systems we depend on, and how prepared we are when those systems change. Because they will change, not eventually, but continuously. And in that continuous change lies the future of both water and human survival. Not in control, but in understanding. Not in elimination of risk, but in awareness of it. And ultimately, not in separation from nature, but in coexistence with its most powerful forces.